presentation, we'll talk about ferrofluids, also showing something aligned.
Thank you, Cristiano, and thank you all organizers for giving me the opportunity to speak here. So my name is Reinhard Richter and I'm from the University of Bayreuth. Do I need to have this phone? Is this important or not? It's important? Okay, good. So what you here see is the landscape of magnetic liquid, and this is one part of what you are going to hear now and in the next two lectures. So I told you I'm from Bayreuth. This is a small town somewhere in the south of Germany, and of course we have their winter. So from the winter to the ferrofluids, what are ferrofluids? Ferrofluids are essentially some black liquid like you have here. So be careful. They are very dirty, and it's always good to have a black shirt on if you start an experiment. And ferrofluids are nanotechnology from the early 1960s. They are a colloidal suspension of magnetic nanoparticles in a carrier liquid like water or silicone oil. And you see that these particles have a diameter in about 10 nanometer and then some cover from, for example, a molecular coating, some tensides, or they have some charges on it. And this prevents the particles from sticking together. And in this way, these particles are not aggregating and not falling out of the liquid. So this is a thermodynamic stable suspension of magnetic nanoparticles kept stable by permanent kicking of KBT. And here you see Ron Rosenzweig in his use when he was starting to prepare these liquids. There were some other people at that time which started to synthesize them. The production in the Transylvanian way was taking huge steel balls, put your magnetite particles into these tubes and rotate for months. And you have to be very careful to put the proper amount of tensides to it. Otherwise, these particles, which are you grinding, would stay forever together. So you need this cover. Nowadays, mostly this stuff is produced in a chemical way, chemical precipitation, like the color-Fala reaction, which ends up here in magnetite, is not so difficult. And this setup is in our lab. So actually it was performed by a chemist, but we have also a chemical lab in physics. And it was actually a student from Mexico who did part of his PhD in my group in Germany. So these particles or these suspensions behave superparamagnetic. That means that the particles itself are ferromagnets, but if you have them in a suspension and you apply a magnetic field, well, first you don't apply a magnetic field, first you see they are kicked around and you don't have any netto magnetization. But then, if you are increasing alpha, which is the Langevin parameter and measures the magnetic dipole moment times the magnetic field over KBT, and if you are increasing alpha by, for example, increasing H, you see that more and more of these particles are getting aligned in the time average, and eventually all magnetizations are pointing to one direction, and you get the saturation magnetization, which is the volume fraction of the particles in your soup times the saturation magnetization of the solid stuff, for example, of the magnetite. The volume fraction is divided by the volume of magnetic material over the overall volume. And for identical particles, you get this kind of function for the magnetization. So this is a Langevin function. So you see this is a cotangent hyperbolicus of alpha minus 1 over alpha times saturation magnetization of the times saturation magnetization, or times V times MD. So, but this is only in an ideal case, because as you see here in a transmission electron picture, you don't have monodispersed particles, you have a distribution of particles. So what you here see is a measured curve of the magnetization, and here you have the magnetic field applied, and the blue curve, well, actually the dots are the data, the experimental data, and the blue curve is the result of a superposition of several Langevin equations, and by doing this proper superposition you get out here the distribution of the particle size. This is one method to get to a distribution of the particle size. And you see that there is some maximum around 6 nanometer for this so 6.3 nanometer, and this is the width of the distribution actually, and so on. So you see the reality is a bit more complicated. And this is saturation magnetization, and another important value is initial susceptibility. This is the steepness the magnetization is starting in the beginning. Well, I told you that this stuff is super paramagnetic. That means it is a bit like paramagnetic, but much stronger than a standard paramagnet. Probably you know a liquid, a paramagnetic liquid. The strongest natural paramagnetic liquid is liquid oxygen. It has an initial susceptibility of 3 times 10 to the minus 3, I think. And so this is, for natural liquids, rather strong. For our superparamagnetic liquids, we have susceptibilities in the range of 1 to 10. So not 10 to the minus 3, but 10. So you have 4 decades. So this is the reason why it's called superparamagnetic. And as you know, paramagnets are attracted to regions of high field strength. So if you want to produce a defined field gradient, it's nice, for example, to take a current conducting wire here, and whoops, that was too fast. And then you see, you know by Biot-Savart, the field is the current over 2 pi times r. So the field is increasing here as you come more and more to the center of the current conducting wire, and it's falling off if you go away. And this is what we did. Here you have a movie. Does it work? Yes, it's good. Okay. So the current source makes 150 amps, and you see that now the ferrofluid is attracting along this current carrying wire, and that is due to the gradient magnetic field. So this is a proof that this liquid is really super paramagnetic. And this 150 amps is something you are getting from a welding current source. It's not so difficult actually. But you have to take care not to keep it running because the wire is getting hot. So if you look, if you are interested why actually this liquid is creeping up this wire, you can have a look at all important energies which are here active. And you have this overall energy is a sum of the hydrostatic energy. This is the first term. This is density times gravitational acceleration and integral over height. And this is the volume. And then you have the surface energy, which because you have a stress about the surface tension, and you have some surface to take into account. And then of course you have also a magnetic field energy. And this is minimized, and if you do this minimizing, you get a shape out of it. The shape of the height here versus the radius is approximately 1/2 over, and this is a constant, and this is susceptibility, and g is again the acceleration times h to the square. So, and this, if you plug in some knowledge here, you end up as a function approximately 1 over r to the square if you are going into the initial regime. In the saturation regime, it's 1 over r. So you see that by knowing these terms of energy, you can really say something about the eventual shape of this stuff. And this is what we will deal with later in a few minutes in more detail. Well, Maxwell has been asked, when he was working with electrons by the British Lord Chancellor for Finance, why are you working with electrons? This is stupid. Nobody knows electrons. It was in 1870 or so. We have all the steam explosions and our steam vessels are exploding. You should do some applied things, calculate the strength of a steam vessel. This is a constant, as a scientist in fundamental physics, you're always asked, why are you doing that? And there are two answers. One answer is, Maxwell's first answer was to the finance minister of Britain, British Empire, one day you may tax it. And actually you're paying tax on your money for electricity today. Another thing is, better answer maybe is, what is a young born baby good for? We just invented, we found something new, and we don't know yet what it will look like, or it will be important for when it's grown up. And that is, of course, I think something which is very important, that fundamental science has not to have a reason for it. Anyway, because this question is so fundamental, I will also ask you, what are ferrofluids good for? And well, there are very important applications nowadays. For example, this magnetic sealing. There are different companies. Ferrotech is a well-known company, and you see that here you have a rotary feed-through, and here you have a magnet, and then you have some iron parts, pole shoes, and they create you a kind of magnetic circuit here. This magnetic circuit has some weak points here, and here I make a zoom, and you see at this points, ferrofluid which you put in here will be attracted due to the field gradient to these positions. And now you have a liquid sealing And this is very important because it is a clean sealing. You can use vacuum pump oil. Thank you very much indeed. You can use vacuum pump oil, and then you have a very clean sealing. And this is used, for example, in your hard disk drive in here, or it is used in semiconductor industry if you pull all this silicium bars out of a melt. So it's a very important technology. This is a magnetic circuit. Well, then there are other important applications, especially in a hot area like here. You need some cooling of your cars. And you know that the old Beetle had some air cooling, it's not so efficient. The more modern Golf has water cooling, it's more efficient, it has more power. And if you want to increase the power of your loudspeakers in your car, you also need liquid cooling. And this is what ferrofluids are used for. You put in the ferrofluid here in the gap of the pole shoes, and then it takes care that the heat produced in these coils is delivered to the housing and then distributed. So this is an active, well, it's not an active cooling, but it is a liquid cooling. This is also a very important commercial application. Then you have magnetic dampers. These are essentially boxes where you have a magnet like this red area, and this is immersed or covered around by ferrofluid, and this damps some motors. And you have something not so serious applications like a ferrofluidic display where you can switch on individual coils, and here it shows the word oil. And of course, most important, ferrofluids are making fun. They are also have an application for funny things, and even you can sell fun. Here you look at a science shop, and you have a completely useless pen holder, and if you put in your pen, a magnet is switched on and or pushed out of a housing, and its ferrofluid is attracted by it. So this is a German nanotechnological invention. You see here, made in Germany still. Something more important with this attraction to the gradient magnetic field, what you have seen right now, is important maybe for your personal future, is magnetic drug targeting. So you can bind magnetic drugs to the magnetic particles, then you apply a gradient magnetic field, and by this you can concentrate your drugs in a tumor. And that is very helpful because then you can, you don't have to harm the usual part of the body by this, and the side effects are much lower. And this is actually used by a lot of several different groups. It's a very active field, and one of these groups, I know this is the group of Professor Alexio at the University of Erlangen, not so far from Bayreuth. And there you see you have such a coil, and the patient has to lie around it. Here you have a leg of a rabbit, and this rabbit somehow survived. So, well, it survives the treatment, but later on it's killed, of course, for analysis. But it has been applied also to humans. So it works, but it has some side effects one has to take care of, and that is that the magnetic particles might block your circulation system. So there's still a lot of research on the way. So this is the question, why, what is it good for? But the main answer is, of course, because it is fun. And after this fundamental introduction, I want to show you my program for the next 2 days. So today we are focusing in the morning on growth and form of ferrofluids, and then we will continue with flow in ferrofluids, And eventually we are investigating magnetic soft matter, ferrogels and so on. So let's start with growth and form. And now, the last year, 2010, was the year of 150 years of Darcy Wentworth Thompson. He wrote a famous book on growth and form, which was maybe a very important step for quantitative descriptions of natural phenomena, especially also in biology. And so I choose the title on growth in form of ferrofluids because we also try to be very quantitative. Next slide, please. Here it is. So in 1967, there was an important article by Martin Cowley, like the cow, and Ronald Rosenzweig on interfacial stability of a ferromagnetic fluid. And you see this nowadays older gentlemen on occasion of a small symposium we've had at the University of Loughborough in 2007. So this is what we are going to do now. Here you have a pair of Helmholtz coils, this upper part and the lower part, and here you have a dish, and I'm now going to fill this dish with a ferrofluid. For that purpose, because I don't have a black pair of trousers, I need to wear the coat. And maybe that gives you also a kind of break. You hear a lot of information today. Then I wear these gloves. And you see it's going to get dirty. This is my pipette. Very important that you have some support for that. And this is the black liquid. So, and I should start a program somewhere. It's difficult to use these gloves together with the computer. So essentially you see here now a vessel, a dish, petri dish. Well, it's made from Teflon, it's a bit more convenient because of the cleaning. And then I'm now pouring in some liquid. And here you have some kind of illumination system. Oops. 3 times 4 milliliter. It's 4 times 4 milliliter. Times 4 milliliter. So that should do it. Let's see. This is a very, how to say, good fraction. It's a collection of old liquids used for scientific experiments, and by evaporation, because the carrier liquid is kerosene, it's getting better and better. It's like an old wine. So, something like that. Okay. That should do it. And now I'm increasing a bit the quality of the picture maybe. Okay, that shows it. Now I'm increasing the magnetic field. You see just the reflection of the ring. Then now you see something popping up. And due to the reflection of the ring, you see now that actually some round objects are popping up. And now I'm increasing the field even more. And now you are seeing a kind of hexagonal arrangement of liquid hills. The best is of course to see it from the side, and you are free to see it downstairs later up in the top. I'm increasing the field even more. And now you're seeing that these kind of spikes are more or less standing on the dry liquid, on the dry surface. And if we wait for a time, then all liquid is sucked up into these spikes, which you can see here a bit better maybe on the side. And the purpose of this demonstration is twofold. First of all, it's difficult to observe optically. This is why there was for a long time not much progress in this field in a quantitative manner. And the other thing is, of course, it's getting totally fast, very hot. The other thing is that after all, it's not so difficult to observe the effect. I mean, to measure it is something else. So I'm going down again with the field. And I'm going now in this range where everything is covered again by ferrofluid. Now you see one and another spike is vanishing, and eventually we have some left. That's gone. So that's for the moment. Not yet. Yeah, I left this camera in Germany. I mean, it was a bit of lack of capacity. But I give you a more side view soon. So this is what we have seen right now, and this is now what is our topic for this morning. I want to speak on growth and form of these ferrofluidic patterns, and the first part deals about the growth, and then the second part is about the form, and then we have kind of combination of growth or decay and form. It's a nonlinear dynamics. So growth is something what Plato is saying. You know that in the beginning, is the most important part of any work, especially in the case of a young and tender thing. For that is the time at which the character is being framed. So the growth of such a pattern is very important for its understanding. And here you have the beach in Obertuba, and you know that water has a special dispersion relation. The dispersion relation of water is combining some term G times K. K is a wave number, and another term B times K to the third power. This is this B is essentially the surface tension. So this part describes you some small tiny capillary waves. These are the small tiny waves which are determined by the surface tension of the liquid. So that means this part is important if lambda is small or if K is large, because then K to the third power is getting large. If K is small, it means that if lambda is large, this is unimportant, because if you have something small, 0.1 times 0.1 times 0.1 is getting smaller and smaller. So this part is really only important for large Ks. And the other part of the dispersion relation are the gravity waves, and they are important for large lambda or for K small, because 0.1 is much more important than 0.1 times 0.1 times 0.1. Okay, this is a standard dispersion relation for any kind of Newtonian liquid, but what we have in addition here is a red term, and this red term is due to the magnetic field, and it's only important for magnetizable liquids like ferrofluid. And I show you now what's going to happen with this dispersion relation if we increase B. The blue, here is omega to the square, and plotted versus K. And the blue part is where B is 0. Now we are increasing B, and at a value of around 0.9 of a critical field, you see that here we're getting some horizontal part, and that is because we are subtracting this part here, and eventually you are subtracting more and more from this blue curve, and you get in here a minimum, and this minimum is actually then touching the horizontal axis at a critical value Kc. This is the capillary wavelength, and it's only determined by the density, the G, and the surface tension. It's not determined by any magnetic parameter. This is the capillary wavelength. And now if you're increasing the magnetic induction and further, you see then you are getting the red curve, unstable here. The red curve has a negative contribution in this range, and that is the strange that you have something to the square which is going to get negative. And this can be interpreted in terms of a growth rate. So if you see that if omega to the square is getting negative, that means it must have a real, an imaginary part, omega 2, and no real part. And if you then have a small amplitude and you plug in this imaginary part, it will evolve in time, that if you have imaginary part and another imaginary part, this cancels off, and essentially you get an exponential growth. So if you plug in this imaginary part in a linear stability analysis, you see that this tiny disturbance is actually growing in time, and these liquid spikes are popping up. And we ask ourselves, as you see here, the minimum somehow should depend on the amount of magnetic field you are applying. So if you are applying higher values of the magnetic induction, then this minimum should be shifted to some range here. And if you apply lower one, it should be here. So if you do this in a fast manner, you should be able to measure some specific wavelengths of this growing pattern. And this is what we did. We switched on suddenly the magnetic field from an undercritical to an overcritical value, and here you see how some liquid disturbances, some liquid ridges are emerging, and then we measured the distance from these liquid ridges, and from that you can extract the wave number of maximal growth. And here you see red plotted is, or actually the data are plotted as a wave number of maximal growth for different fields where you are jumping to. And what we could see of proof is that actually the wave number of maximal growth is dependent, essentially linearly dependent on the magnetic induction. And there was a long-standing controversy on this subject, because people in France, for example, they measured that the wave number of the pattern evolving is constant and does not depend on the field. And that is true if you look at the final pattern. But for this final pattern, you are far away from this regime where some linear stability analysis is valid. And for the final pattern, you need non-linear techniques. So you cannot compare apples with pears. You have to compare some linear stability analysis with some proper experiment in the regime of small amplitude. And this is what we did. And Adrian Langes, our theoretician at that time in Magdeburg, he solved the dispersion relation for some specific, taking into account the finite depth of the liquid layer and also the nonlinear magnetization. And this is what you see in here, this red line. Okay, so we can understand the wave number of maximal growth in the early time or in the early stage of our pattern. Now we are also interested of the maximal growth rate. How fast is our child going? And there are some predictions from Adrian that there should be such a kind of scaling of this growth, where B hat is some kind of rescaled quantity for the magnetic induction. And as you have seen, if you switch on the field fast, then your pattern will also go up very fast. Within some 80 milliseconds or so, the pattern is already there. So we had to develop a technique to measure the amplitudes of this pattern quantitatively in a fast manner. And you cannot do this from optics because you don't know how high such a spike is from optics. So what we measured is the magnetic field in this kind of center array. Here you see some Hall centers, and they are in a vessel made from transparent perspex, and they are mounted immediately under this vessel. Now if you have some liquid ridges, this is modifying the field lines, and you can relate the height of the ridges with the kind of focusing of the magnetic induction. And this was connected to a PC, and so we can measure with 7 kilohertz, 7,000 measurements per second, and we can measure now here the growth of this amplitude, and you see that depending on the field, you have a jump in the height and then an oscillatory kind of evolution until you have a final stable height. And this is measurement, and that is numerics from finite element methods. And from that curve you can extract now the early stage by fitting exponential functions, and from this exponential functions you get the maximal growth rate. Now we have a comparison of experiment theory and numerics, and if you compare theory with numerics and with the experiment, it's not so convincing actually, but the numerics fits quite well to our data. We have kind of intuition. What is the reason for the discrepancy? The discrepancy is that the pattern is not evolving homogeneously over the range, but is starting at the edge, where you are creating an inhomogeneity in the magnetic field due to the final size of the vessel. And that might be a reason for this discrepancy. Now we have had a look in some results on the growth behavior, and now we are going ahead in time to the adult phase of the pattern with 18 or so, and we have a look at the stable nonlinear patterns. So the advantage of such a kind of experimental system I'm showing here you today is that it is essentially a system without permanent energy throughput. That means you have an energy functional which describes the system. And this energy functional comprises the hydrostatic energy. This is the first term. This is just that it's heavy to lift something up. And then the surface energy density. This is the third term, which describes you that if you're producing some additional surface, it costs energy. And then, of course, both of these terms are increased during the transition. But why should now this pattern evolve if you have to invest energy? And the reason for that is that this investment is overcompensated by a gain in magnetic field energy. And this is this part. And this gain is due to that field lines can be focused in these spikes, and then if you have field lines going for a longer time in the magnetic liquid, due to the high susceptibility of the magnetic liquid, really it pays off, and the magnetic field energy can be reduced. So by minimizing this energy functional, some amplitude equations have been presented, and here you see such an amplitude equation that says that the change of the amplitude in time should, at the final state of the system, be zero, and what you get out is such kind of equation for where you have an a term, a to the square, and a to the third power, and epsilon, which is giving you the bifurcation parameters. This is essentially the magnetic field. And I have plotted you the solution of this amplitude equation. And so here is plotted the amplitude. Here is essentially the magnetic induction. And now I'm increasing the magnetic induction, and you see that we have a flat surface. And then there is a critical point where the flat surface is getting unstable, and we have to jump to the next stable branch, and this is this continuous line. This is describing the solution of hexagons. And if you are going up, these spikes should grow, and if you are going down back, you should stay on such a spike in a more longer time. There's also such a pattern, and eventually this hexagonal pattern should vanish again. And there is a difference described by this hysteresis. These are people, Galitis in 1977, René Friedrichs and Andreas Engel in 2001, and Stefan Bolius, Helmut Brandt and Harald Kleiner contributed to this theory of the system. Now, once you have such a model, you want to test it quantitatively. And how you have access to this amplitude in such a dark matter? Well, as you know from Superman, it's always helpful to have X-rays, and we are using that method. That we have here a kind of we have an X-ray tube, and with this X-ray tube we are illuminating our pattern. And those X-rays which are penetrating here, the spikes, are more heavily absorbed than the others which are penetrating only the valleys. So there is not so much material. And you get here kind of absorption picture, and so the dark spots are responsible for the spikes. Now you can take a known object like a ramp or filled with ferrofluid, and you can calibrate that, and then you are done. In the lab it looks like that we have a tower where we have a X-ray tube with a tungsten anode. Here we have the Helmholtz coils, and beyond we have it's in here we have a very sensitive detector with 16-bit resolution in that direction. And the outcome of this measurements are such kind of mountains. Here the black lines are describing you 1 millimeter height difference, and the color is coding the height of the system. Now we are able to measure the height of a spike in the center of the pattern, far away from any disturbances from the edges. And you might have seen such mountains before. Well, we plot here the amplitude for increasing magnetic induction, then we plot the amplitude for decreasing magnetic induction, and you see a tiny hysteresis. Now we want to know how is the quantitative description of such behavior. This is one of our students, Christian Gorbitzer, who performed this measurement. And to give you a quantitative description, you can of course use these amplitude equations, but this is only semi-quantitative because they cannot give you the proper factors for your specific liquid. So we ask our colleagues Lutz Tobiska and Gunnar Mattis at the University of Magdeburg, and now in Kassel, Gunnar, and they solved the Young-Laplace equations on a hexagonal mesh. The Young-Laplace equations are giving you the surface tension essentially, and then they coupled Maxwell equations taking into account the Navier-Stokes equations on a 3D mesh. They solved the fourth level, 400,000 of unknowns, and as an outcome you get such a spike And you see that on top of the spike, the red area is where most of the material is highly magnetized, and at the bottom, it's blue area, there's the magnetization not so high. So this is very important. And now we plot this height of the spikes, and you see it nicely fits with our experiments. But it fits only if you take into account the really non-linear experimental magnetization curve. Then you have solved the question. I hope you are not offended, because probably most of you will be Paulistas. Anyway, I once was there on this hill, and it reminded me of our structures. Now we have a look at the shape of the spikes. You can cut through such a spike, and you get a cross section. These are the blue dots, and the finite element method gives you the red line. So you're quite happy with this agreement. And now you can plot these cross sections of these concavenados on top of each other and rescale the height. And you see that here, in the experiment, you hardly see a difference. That means that the structures should be somehow self-similar. But this caused a lot of discussions, because there is not a real reason for such a self-similarity. And if you look at the simulations, you see these deviations. So actually, it's not really a true something which is important, that these spikes are in standard not self-similar. But what you learn out of it, that they are rather similar for a certain amount of liquid, type of liquid, and that is, if you look at the two-dimensional power spectrum or two-dimensional Fourier transform, and here you have the height, and it's logarithmically plotted, you see that the main power are in these 6 towers. So these are the fundamental harmonics, and there is the main power. And this explains you why this pattern looks almost self-similar, because you have the main power in the fundamentals, in the harmonics. So essentially for this liquid, it's kind of harmonic pattern. A sinus with different amplitude is always self-similar. So it's trivial here, but it doesn't have to be for all kinds of liquid in that way. Now we go to higher fields, and if you're increasing the field and you have a certain amount of liquid, you can't see here because here I have only a shallow layer, and essentially then you see the bottom of the layer. But if you have a thick layer of 1 centimeter, you can increase the height further, and in agreement with the predictions, there should be a transition to another branch where you have S squares. This is dashed branch, which is unstable, but then it's becoming stable, and there should pop up some squares. How these squares are popping up is not really known. Well, let's have a look. Well, you see here a measurement, but this measurement has been processed. The tip of the spikes are the black dots, and then you calculate around each tip of a spike the points which are nearest to the maximum. So these are the nearest neighbors. This is something called a Voronoi decomposition. And then you can color code these tiles, and we are using this color code, which is saying that the maximum central angle, which is giving here from the angle from the tip to some kind of corners here, the maximum central angle is defined using color. So as you see here, you have some kind of pentagons. They are almost yellow. The hexagons are green, the heptagons are turquoise and so on. So I'm increasing the field, and I show you now certain values. Here you see such red areas are popping up in patches. So here you have almost square-like cells, and the amount of these cells is increasing, and eventually everything is more or less square-like. So this is something which has been described by Abu in 2000, but without taking use of the height information. And taking into account the height, we can go on further. And from this Voronoi decomposition and the central angle, we can calculate the angular correlation function Q6. And Q6 is 1 if you have a hexagon, and otherwise it's 0. And Q6 is averaged over all such cells. Well, this parameter is plotted, Q6 versus the magnetic induction. And those of you which are familiar with magnetism would say, okay, we have a hysteresis. Fine. But if you look more carefully, hysteresis is hysteros. That means afterwards. So, in a hysteresis, you always want to stay as long as you can at the place or in the state where you are. You look now at the arrows, and this is not the case. This would be a hysteresis going down the blue line, going up the red line. This is a standard hysteresis. We didn't see that. We found that it wanted to go as early as possible away and come back as early as possible. This is the opposite of a hysteresis, a proteresis. And so we didn't understand that. And there is no reason for that behavior. I mean, from the point of theory, you cannot understand it. So we said, okay, maybe the reason is that here our system is not large enough, and we performed the second stage of the experiment. And this experiment is the paella pan project. We bought a huge paella pan with 40 centimeter diameter. And why we bought the paella pan? Well, you get a very flat, well-defined pan for almost nothing. It's covered with Teflon. It's good because you don't waste your ferrofluid all the time. So you can empty this pan again, and then we put this huge pan in a large magnet, and we measured again Q6, and here is another measure which is similar to Q6, which gives you the circumference area ratio. And now, if you look at this large system, you have a proper hysteresis. So you're going down late, and you are going up late. So we are quite happy because we realized that by the side wall forcing we had some artifacts, and that gives you a lecture that you never can make the system large enough. And what we did in addition here is, I have to go, probably I skipped that. Yeah, I skipped it. Anyway, we continue. So these large systems are important, and also the behavior at the edge of this system. Now I want to proceed to ridges and stretched hexagons. So far our field was going up. So the system was isotropic. So the system here doesn't feel any orientation because the field is vertical. It has no preferred direction. And now we are going to apply a small horizontal field to change the direction of the field. And this can be done by an additional pair of field coils applying a horizontal element. Of course, the combination of both fields give you a tilted field. Well, it's tilted that way, okay. So, and now there was a prediction by our colleagues from Magdeburg that once you have such a hexagonal pattern and you are applying in a proper way a horizontal field component, then there should be a transition to liquid ridges. And now I'm switching on the horizontal field component. I'm increasing the field, and you see now an X-ray movie, and the red areas are the tips, and you see that the tips are now tilting, and eventually the tips are gone, and you have this liquid ridges. So okay, we were quite happy, this prediction was fine, and we looked at this transition for different fields. So we were increasing for different horizontal components, the vertical component, and we measured this transition from the flat range to the ridges. And this can be nicely be described by some very elaborate dispersion relation. You see again here some k and some k to the third power, and then you have these huge terms here which have to deal with the nonlinear magnetization curve. But it can be done, and you see that the blue line fits nicely with these measurements. But then we did something very mean. We asked ourselves, how does the pattern know what the experimentalist wants to do? When once I have a hexagonal pattern, the pattern has no idea in which direction I want to apply my horizontal field component. And what happens if I don't stick to the rules and don't follow the direction of the field component as suggested by René? I have shown you here. This. Here, the field component was along the diagonal of the hexagonal pattern. And well, we said, now we do it in a mean way, we do the field component to that direction. Now, how will the pattern react? And I'll show you the outcome in the overview. Here you have the pattern and the hexagons, and they are now with a diagonal against this direction, orthogonal to this homogeneous field. And here you see the black stuff is here with these 6 points. It's a two-dimensional Fourier transform. So you get for hexagonal patterns this orientation. Now we are increasing the field component, and then you see something is taking place. Eventually you have a kind of reorientation of the pattern. Here some new maxima are popping up, and you see that now the hexagons have flipped. And then if you are increasing further, these flipped hexagons do as predicted, they give way to liquid ridges. So we said, oh, we have a new transitional hexagon flip, how can we understand that? And I went down to Professor Friedrich Bussig, quite famous for convection in Bayreuth, and he is the man who worked for the last 30 years with hexagons, and during one night he wrote down a set of amplitude equations, and you see here you have some red hexagons and you have some blue hexagons, and even he plotted here the behavior of these amplitudes, and later he came up with some numerical model, solution of these amplitude equations, and we showed, well, we looked at our measurements, and you see that here you start with red hexagons. These are these transversal modes. This is the amplitude of this T mode and the C mode, and then at this point this hexagon is flipping, the amplitude is going away, and it's popping up a new blue amplitude, the blue hexagons going up, and the green one's amplitude is describing you the liquid ridges, and so we have this amplitude and this amplitude describing a hexagon, and eventually the blue amplitude is vanishing, and you end up with liquid ridges. And this is what actually is recovered here also in the amplitude equation. So we are quite happy about that. And we can be mean to an hexagon, it always finds its way to reorient in a proper way. When it's finished, how much time do I have?
I think it's better if you finish this. If you want.
Yeah, I think after lunch or in the afternoon, I would like to continue with the nonlinear dynamics part, and then give you an idea of how to control flow in ferrofluids by different types of magnetic fields. I thank you very much for your attention. And you are very welcome to push the buttons here in front.
So questions?
I'm not a professor yet, I'm a Privatdozent. This is a multi-layered structure in Germany. Spikes.
The lateral distance between the Finegels.
The lateral distance is very boring. Of the nonlinear pattern, it almost stays. I mean, if you look into theory, it's slightly decreasing with high fields, but these are only calculations for infinite layers, and then you have to take into account a finite layer. But from our measurements, I have not shown you this because it's boring, more or less. Yeah, they behave very smoothly. So the real music is in the amplitude.
But the viscosity of the fluid could play a role in this distance between the spikes.
The viscosity is important for the go state. For the final pattern, it is really of minor, if not at all, of any importance. It is, I would say, of very minor importance. Yeah. I showed you 3 papers, and 2 of them are based on the minimization of the free energy functional. And this is a very nice technique, but has also its shortcoming. And then there is a very new approach where a group from Mainz and Bayreuth solved the so-called adjoint problem for surface systems. Like Marangoni convection is also in this value, in this range. And they solved this by taking into account not only the final pattern, but also the evolution of the pattern, and taking into account in a weakly nonlinear description, they can go further. But these are fundamental theoreticians, I would say so, and they are not yet, they know everything how to do it, but there's still a lot of work ahead to do it for one specific liquid. And for that, we need support from other theoreticians as well. And it seems that Adrian Lange, now at the University of Dresden, is helping us. And I think with this breakthrough of this solving of this adjoint problem, we have now a new basis for very quantitative comparison of amplitude equations with high resolution measurements. More questions, please? Yeah, and I'm very happy that the noise level is decreased now.
So let's then again.